All right, so welcome to the Generalized Linear Models Part 2. We're just gonna touch upon a couple of things. First and foremost, we're gonna start with a quick definition. And this definition is that y is a random variable from the exponential family if the distribution can be written as, in this case, we're going to have f of y given theta and phi. This is going to be the exponential of y theta minus b of theta divided by a of phi plus c of y comma phi. Okay, so again, a little review. Theta is known as the canonical parameter. And phi is known as the dispersion parameter. Okay. So let's do a little bit of math now. Let's call this example number 1. We want to show that y is a member of the binomial distribution for some n and p such that n is known and is a member of the exponential family. So in this case, we are going to have f of y given n and p. This is going to be the probability of y equaling little y given n and p. This is n choose y, p to the y, 1 minus p to the n minus y. And this is going to equal the exponential of the log of n choose y, p to the y, 1 minus p to the n minus y. Okay, and then we can expand this out a little bit. Here we have the equal to the exponential. Give me 1 second. This is going to equal to the exponential here of, now we're going to have the log of n choose y plus y log of p plus n minus y log of 1 minus p. And this is going to equal to the exponential of y log p over 1 minus p plus n log 1 minus p plus the log of n choose y. And then looking at this here, this right here, this gives us our theta. This right here gives us our b of theta. And this here gives us our c of y phi. And then something else to note, that theta is equal to log of p over 1 minus p, and also that a of phi, this is going to equal to 1. Okay, so let's look at a couple of takeaways from the problem we just solved. The first takeaway would be that the response must be from the exponential family. Why? The second takeaway, the canonical parameter always plays a role. And the third takeaway is that many of the common distributions, example binomial, Poisson, normal, and exponential, are from the exponential family. Let us now look at another example. This time we're going to be looking instead of the binomial, we'll be looking at the Bernoulli distribution now. And also something to note that earlier on, this was got a close parenthesis, so the parenthesis closes over here. All right, let's look at the next example. Okay, now let us look at the Bernoulli. So suppose that y belongs either between 0 and 1, and we model the distribution of y given x as Bernoulli with success p. In other words, 1 with probability p and 0 with the probability, this one's going to be 1 minus p. If this is the case, therefore, the PMF, which stands for the probability mass function, and not a density since y is discrete, so I'm going to put here not a density, since y is discrete. This is going to be, we're going to write this as f of y is equal to p to the y, 1 minus p to the 1 minus y. If this is the case, then we can rewrite to fit the exponential family form as f of y. This is going to equal to the exponential of y log p plus 1 minus y log 1 minus p. And this is going to equal to the exponential y log of p over 1 minus p plus log of 1 minus p. As you can see, this looks very similar to our binomial. Very, very similar. Okay. So with that being the case, we can now identify theta. Okay. And what's our theta going to be here? We can identify our theta as log of p divided by 1 minus p. Okay, and this is, we can describe this as our natural parameter. So note that here, this means that mu is going to equal to p. And using the inverse of the above relationship, we can directly write the mean p as a function of theta, as in p is going to equal to e to the theta divided by 1 plus e to the theta. Okay. Give me a second, let me write p. Again, 1 second here. Now, if this is the case, okay, we can go ahead and say that b of theta is going to equal to the log of 1 minus p, okay? And this is actually going to equal to negative log of 1 plus e to the theta. All right. And then another caveat here that you should note is going to be that there is no dispersion parameter. So we can set a of phi as 1 and c of y of phi as 0. Okay. Now we're done with the Bernoulli. Let's move on now to the Poisson. Okay, so now we are dealing with the Poisson. So for the Poisson, let's suppose that y belongs in 0, 1, 2, 3, etc. And let's say, in other words, this means that y is a non-negative count. And we model its distribution. And we say here conditional on x as Poisson with the mean mu. If this is the case, then its probability mass function is going to be f of y is equal to 1 over y factorial e to the negative mu to the y. And then we can rewrite this, and we're going to end up with f of y is equal to the exponential of y log mu minus log of y factorial. So now that we've gotten into the exponential form, here we can say that theta is equal to the log of mu, and we have this as our natural parameter. Reciprocally, we can write the mean in terms of the natural parameter as mu is equal to e to the theta. Therefore, we can say that b of theta is equal to mu, which is equal to e to the theta. And last but not least, again, there's no dispersion parameter. So we can write and set a of phi. We can set that equal to 1. One second here. The a is not coming. There we go. We can set a of phi is equal to 1. And then finally, we can set c of y phi, this is going to equal to negative log of y factorial. Perfect. All right. So this takes care of the Poisson. Now let's go and look at the Gaussian. Okay, welcome back. So for this portion of the lecture, we're going to be looking at the Gaussian distribution. So we begin by saying that a familiar setting is probably when y belongs to the reals and we model y given x as the normal distribution, mu sigma squared, okay? Therefore, we can say that the density is going to be f of y. This is going to equal to the exponential y mu. Actually, 1 second. We're going to say f of y is equal to 1 divided by root 2 pi sigma. And now we're going to have the exponential of negative y minus mu squared all over 2 sigma squared. Okay, now this is pretty much already an exponential form, but we can simplify this by manipulating it a little bit, okay? And you don't have to memorize the steps to this. You just have to understand or be familiar with the final form here. And that we have f of y is equal to the exponential of y mu minus mu squared over 2, all divided by sigma squared minus y squared divided by 2 sigma squared minus the log of sigma minus the log of root 2 pi. Okay, so now in this form here, we can look at this and we can sort this out. Okay, we know the natural parameter now. Natural parameter. This is going to be theta is equal to mu. And b of theta is equal to theta squared over 2. And then for our dispersion parameter, we have that phi is equal to standard deviation, okay, the spread. And we have that a of phi, this is equal to sigma squared. And in that case, then with c of y of phi, this is going to equal to y squared divided by 2 sigma squared. Give me 1 second here. My touchpad does not like to write the number 2 for some strange reason. We're going to say this is going to be y squared over, sigma squared, 2 sigma squared, minus the log of sigma minus the log of root 2 pi. So again, the natural parameter theta is equal to mu. B of theta is equal to theta squared over 2. Dispersion parameter phi is equal to sigma. A of phi is equal to sigma squared. And C of y phi is y squared over 2 sigma squared. minus the log of sigma minus log of root 2 pi. I would like to quickly point out that the C of y of phi, I made a mistake. There should actually be a negative sign here. So just make sure to put that negative sign in there as well. So again, we just looked at this example right here. And something to note as well, just like I pointed out earlier, is that C of y, phi, there should be a negative sign right there. Okay, wonderful. So let us ask ourselves a couple of questions. What about the link function g? Okay, well, we've already seen that for the normal case, the right choice for the link function is the identity transformation. G of mu is equal to mu, such that we model mu is equal to beta transpose x. And for the Bernoulli case, the right choice of the link function is the legit transformation. G of mu is equal to log of mu over 1 minus mu. So that we model log of mu over 1 minus mu as the value of beta transpose x. We've already explained that each of these transformations is appropriate in their own context. Recall that mu is equal to p, which is in reference to the success probability in the Bernoulli case. So with that being said, one may ask, well, what about the Poisson case? Okay. Now for the Poisson, just a couple of things I want to touch up on here is that one second. Okay, so we mentioned earlier about the Poisson case, and in general, given an exponential family, one might ask, well, what is going to be the right transform? Well, fortunately for us, there is a default choice of link function called the canonical link. We can define this implicitly by the link function that sets theta as eta. In other words, the link function is defined via g of mu is equal to theta by writing the natural parameter theta in terms of u. In many cases, we can read off the canonical link just from the term that multiplies y in the exponential family density or mass function. For example, in a normal case such that g of mu is equal to mu. For Bernoulli, g of mu is equal to log of mu minus over 1 minus mu, and Poisson, g of mu is equal to log of mu. Finally, the canonical link is general and tends to work pretty well. It's important to note that the canonical link is not the only right choice for the link function. For example, in the Bernoulli setting, another common choice, aside from the g of mu is equal to log of mu over 1 minus mu, is what we call the probit link, which is g of mu is equal to phi inverse of mu, such that phi is the standard normal cumulative distribution function, also known as the CDF. All right, so that concludes our basis for general linear models, and our next lecture will pertain to generalized additive models. Thank you very much and have a good day.